Sometimes we are interested in relative position of value in relationship to other values in a data set, and we can use percentiles for this. Percentiles represent the approximate percentage of values in a data set that are below a certain value. For example, you may be interested in taking a new job and you're offered a salary of $100,000. How do you know if the firm is giving you a good offer? I'm pretty sure that you will be happier with this number if you know that your offer puts you at the 95th percentile, which would mean that you're getting paid better than 95% of others with the similar job titles. You may not be as excited if you knew your salary is at 25%, which means 75% of people get higher paid than you. So percentiles very quickly will inform you about the position of the value you're studying. How do we calculate percentiles? We already know something about this. If you recall, we talked about median, which is the value where 50% of the data points are higher than that and 50% of the data points are less than that. So median is 50th percentile. To find the median, we ordered the data set in order, and point in the middle was the median, or the 50th percentile. So to find any percentile, we do the same. We order the data set for a given percentile, let's say 10%, the data point that has 10% of the observation below it is the 10th percentile. Consider this example where we have data for 10 individual salaries for people with similar job titles as you were getting hired for. I have already ordered the 10 data points in ascending order here. The 10th percentile is between these two values, where one value is less than it, which in this case is the 10th% of the value, and 9 values are more than it, which is 90th% of the values. The 50th percentile is here, and your salary of $100,000 will fall here, which is close to 60th percentile. There are different ways of calculating percentiles, but all methods will give you results that are close. For now, I would like you to understand what percentiles are telling us, which is the position of a given value in relationship to other values in data set. When we have large sets of data, then we have another way of finding the position of a specific observation. This is known as the z-score. By using the z-score, we can find the proportion of data points that are less than a specific value. The z-score is calculated using this formula. Here, x is the variable of interest, mu is the mean for the population, and sigma is the standard deviation. For example, if you were graduating from a college with a degree in business, you get a job offer and would like to know how your offer stacks up against others, all other peers from all colleges with job offers similar to yours. If all you knew is the median, then you can tell if you're in the top 50% or the lower 50%. But are you at 51% or 95%? We can calculate the position of your offer by calculating its z-score. Now let's expand on this example we were using before. You interview for a job and get an offer and would like to know how competitive is your offered salary. All you have is some data based on published reports on websites. Let's look at such website. I'm using payscale.com. Searching for a job title such as business analyst gives the following information. The median is 54,030 and the standard deviation about 8,900. You get an offer of 60,000. This is above the median. But how does the salary stack up compared to others? To know where this salary falls, we can determine its percentile. To do this, we need to first find out how many standard deviation the offered salary is from the mean or the median. This is known as the z-score and is calculated by taking x minus the mean and dividing it by the standard deviation. For you, the x is the salary offered to you of 65,000, and average salary is 54,030. Standard deviation 8,600. This means you received an offer which is 1.27 standard deviations above the mean. How can we tell where we stand in comparison to the rest of the people getting such offer? Is the salary on the top 70%, top 99%? What exactly could it be? Now let me share with you some very useful properties of a bell curve. For large data sets, we often observe that many values cluster around the mean or the median. So if that we create a histogram of the data, we get a distribution that represents a bell shape, a symmetrical curve. When this happens, according to the empirical rule, 68% of all observations will fall within one standard deviation of the mean, 95% will fall within two standard deviations, and 99.7% of all observation will fall within 3 standard deviations. Knowing this rule of 1 standard deviation, 2 standard deviation, 3 standard deviation, known as the empirical rule, will always be a handy way of figuring out where an observation of interest falls in comparison to the mean or the median. So given a specific observation, the offer we received, and knowing something about this type of job starting salaries, we were able to find our relative place in the group. The z-score, when positive, tells you that the value is above the mean, and when it's negative, it's below the mean. Furthermore, it tells you how many standard deviations are you above or below the mean. So the salary offer is between 1 and 2 standard deviations above the mean, roughly around here. So certainly the salary received somewhere in the 70th and 95th percentile. Not bad. In later lesson, we will learn to know the exact value. But for now, we can use the empirical rule as a rough estimate. And this can be very important because many times you're in a meetings where you're being shown a lot of statistics, and if you want to use your judgment to evaluate the validity of what is being recommended or ask follow-up questions and don't have access to a computer or calculator, using this understanding about being 1, 2, 3 standard deviations away from the mean and the probabilities can provide you with a quick insight. The graph you see here is from payscale.com for the salary of business analysts. It is showing the values for the 10th percentile, 25th percentile, mean, 75th percentile, and the 90th percentile. Looks as though the offered salary for you is closer to the 90th percentile. Calculating the z-value of an observation and knowing about the empirical rule helps us determine what percent of the data is below the value we are examining. True Car commercial addresses the question of how do you know if you're paying a fair value for a car you're about to purchase. In their commercial, they do this by showing a visual of the range of prices people in your area have paid for the same car. The mean is at the good market value, and the tails of the curve show below and above the market value. Of course, you would be happy about your purchase if your purchase price is falling in the left side of the curve below the mean and toward the good buy. As an example, I have asked for a price of a new Camry XLE V6 near my office area where I'm likely to go shopping. This is what I get. They have data on 201 sales in my area for a type of a car I'm interested in. The bar graph is the actual histogram for price ranges. Then a normal curve is superimposed on this. The mean of the curve appears to be at the factory invoice of $30,494. Looking at this, most people are paying less than this value. Maybe this is to make sure that everyone leaves the lot happy about the bargain they received. But the actual sold price data shows average selling price to be around $29,000. Furthermore, you see the use of empirical rule without being mentioned, of course, to create the categories of good price, great price, above market, exceptional value. I'm showing you this graph to illustrate the fact that oftentimes in business, the absolute values, such as the price you paid for your car, has lot less meaning than how did the price you paid for a car stack up against others? This is about the relative position of the value of interest. Again, here, that would be the price you paid for your car in the entire data set available. When your purchase price is about 2 standard deviations below the mean, then you have paid exceptional bargain compared to the rest of the people who purchased the same type of car. Staying with the car example, the car you buy has this sticker on its window. This is a fuel economy label. Every new car sold in the United States is required to have a fuel economy label, which shows the miles per gallon estimates. This is meant to help consumers compare and shop for vehicles. So if the best in this category is 32 miles per gallon, that is the 99th percentile, and the worst mileage per gallon is 16, then how does the car you're considering to buy with 26 miles per gallon stack up compared to the rest of the vehicle in this class? This car has an average of 26 miles per gallon, where the range is between 16 and 32. So the midpoint is a rough point estimate of the average for the car in this category, and that's about 24 miles per gallon. We can also get a rough estimate for standard deviation based on the empirical rule. That is, 99.75% of all observations will be within plus or minus 3 standard deviation. Thus, a rough estimate for the standard deviation is the distance between 32 and 16 divided by 6. Remember, we have 3 standard deviations on both sides of the mean for a total of 6. Using this, we will get standard deviation of 2.67 miles per gallon. So this particular car that you're considering is above average and is roughly 0.75 standard deviations above the mean. Now remember that 68% of observations fall within 1 standard deviation, shown here in red. The remaining 32% of the observations are distributed symmetrically outside of the plus and minus 1 standard deviation, shown in blue. So a very rough estimate would be that the car we are considering to buy is close to an 80th percentile. It is 1 standard deviation higher than it would have been. 68% plus 16 would have given you 84th percentile. So I went a little less than that since we are only 0.75 standard deviation from the mean. So as you can see, knowing the z-score can help us determine how to place a particular observation within a population. To most of us, when making a decision, knowing this placement, called sometimes in everyday language as percentile, is much more meaningful than the actual value, such as miles per gallon, as was in this case.